Hi, in this video I'm going to do exploratory data analysis of a financial time series data. I'm going to take the Nifty 50 index data. It's the index data for the National Stock Exchange of India. I'm going to import that dataset first. So before that, I have actually defined my working library, and there in the working directory I have the dataset. I'll first import that, and I'll obviously import first the library that I'll be needing to do the exploratory data analysis. So I'll import the Matplotlib, Numpy, Pandas, Seaborn, and Statsmodel for certain things. So these are standard library needed to do exploratory data analysis of any kind of data, and of course for time series data as well. So I've already imported the data set, but you can simply import it using Pandas, right? read.excel function. I'm going to give you this notebook as well as the data. You can find it in the description section, so you can practice on your own. So let's see how it looks like. Okay, so this is how it looks like. As you can see, I've taken data since 2003. These are the sort of top 5 observations. We've got index prices as well as index return. It's the logarithmic return. Prices cannot be negative, right? You can see all positive numbers, but return can certainly be negative. You can have positive as well as negative return, and that's what you can see here. You can also see the full data set, right? So this is how it looks like. So I've taken data from 2003 to 2004. So it's a 12 months of that, 255 data points. Yeah, it's time series data with regular interval, and that was the nature of a time series data set. I've got two variable, prices and returns, so we will explore these two variables. First, I'll see if there are null values in these two variables. So I'm going to use the isNull function. Let's see. So I do not have null values because it returns false. And then summary statistic of these two variables. So I'll use the by the way, the variable where we have, or the data frame where we have stored our data set, is stock. So that's why it's stock.describe. Okay, let's see how it looks like. The count, we have 255 observations. The mean stock price in the 1 year mean index price is 1236. Return is just 0.2%. That's a very low return. It's real data, it's not simulated data. I've taken this data from the website of National Stock Exchange, so you can imagine the return happening in 2003 and 4. The index return was very low that time. It was just 0.2%. 0.2%. Standard deviation is quite high actually. The index price, it is quite volatile, and you can expect that to happen. And then especially in a developing economy like India, index price would be very volatile. You have a minimum stock price of 924 and a maximum of 1946. Okay, so it's quite volatile, right? You can see the description, the distribution of the index price, and it really appears like it's very volatile, which conforms to the economic theory that the stock indexes and even the stock prices in developing countries are very volatile. And then we'll plot the index, and to do that we will use the Matplotlib. So we have imported the Matplotlib. We'll use the pplot function, so it's a plt.plot, and then we'll use title to just provide the name of the graph. You can give any name. So we are plotting prices first. We will then plot returns, and there are completely two different variables. You will find two different types of plots, and in a short while we'll see that. So this is how it looks like. You can see a good trend, right? It was initially going down, then it gradually went up. So it's an increasing trend. It's not random. It's not random. It doesn't look like random. There's a linear trend, upward trend from May 2003 onwards until end of 2003, and beginning of 2004. So let's then plot the return data, right? The syntax remains the same. We now change the variable. Well, the returns looks very different, right? Because returns, the logarithmic return, right, it can be both negative as well as positive. So it's not linear. You cannot expect that to happen. It's hovering around 0%, right? Sometimes it's positive, sometimes it's negative, and it looks very random. There is hardly any pattern in this particular data. So then what we'll do is that we'll plot both, right? You can also plot both. Syntax remains the same. It's just that you just have to run both code at the same time. When I do that, I get these two graphs, these line plots. Both are we use different colors this time. We have used red instead of the same blue color for return. You can also plot side by side, that's also possible. And then we'll have a dotted plot. Dotted plot is very important, especially for return data, because it's so clumsy that it's the pattern. In case you really want to know if there exists some, it's better to check the dotted plot instead of the line plot. So let's see first how the dotted plot looks like for the stock price. This is how it looks like, but we are more interested to see the dotted plot for the return data. That will be a bit more different than we have seen in the line plot. Okay, the syntax is pretty much same, except the fact that now we use in the plot function style equal to k dot, right? When you use that, then you get this dotted plot. So let's run it for return. For return, you can see that it's quite random. It is hovering around 0%, as we already discussed. You can expect that to happen. And then in time series terminology, we call it as white noise. It looks like it is white noise where you simply do not have a pattern, and you expect that in the return data. And as you see, there are some outliers, no doubt, right? Like this is the one. There are a few in the positive side as well, but otherwise, if you take the average of it, it will be somewhere around 0%. And we have taken that in the beginning when we had this summary statistic, and we found out that the average return is just 0.0%, right? Average return does not mean that the overall return will be very, very different. So don't go by the average return like this, right? Because this is on a return on a daily basis, and then I average it out. That does not mean that if you take the first price data and the last price data and see what exactly is the return is, that's not going to be 0.2%. That is much higher. In fact, it increased quite significantly in the 1 year during 2003 and 4. So something to be very careful about. Then we will create the histograms for these data points. In time series data, histogram is not that important as compared to in cross-section data or in other kinds of data like panel data as well. But in time series data, we certainly can use it for things that we like to know. For example, here in the histogram, you see that for a majority of the time, the prices hovered around 1000 to 1200, right? For most part of the we had stock in the index prices somewhere around 1000 to 1200, and there are only few cases where it went beyond 1600. And then we'll also see the return data for this. So we are using here the hist function, right? The syntax is very simple. You use our data frame and provide the name of the variable for which you want the histogram, and then use the hist function, right? And then we use the Matplotlib to how it looks like, right? So it's just plt dot show. The return looks pretty normal, right? And that also is expected. Whereas prices, index prices is orthotic, is right orthotic, but index is pretty normal, looks very normal. And then we will plot the kernel density. So kernel density is the smooth version of your histogram, and you see it in a line plot, very similar to line plot, but it's smooth version of a histogram. And what we'll do is that we'll use the same function plot, but here that we provide is kind equal to KDE, right? And then for each of these prices and return, we will have separate plots, or KDE plots. So let's run this. So you'll see a smooth version, right? And this is exactly how it looks like. The first one is for prices, index prices, and the second one is for the return. And as expected, the second one, the looks very similar to a normal probability, a normal plot. In fact, it looks like more like normal plot rather than a normal plot, whereas you see that the prices is right orthotic. And then what we'll do is that we will plot the moving average. Well, moving average actually smooths the time series, okay? And that's important to understand, especially if you really want to know how on average is the price or the return is doing, rather than simply worrying about not worrying about these extreme cases that happens once in a while. So smoothing actually, as the name suggests, will smooth the graph, okay? And for that we'll be using the rolling function here, and we will do it for prices and we'll do it for return. Next syntax is that we will be using from the rolling function from the Statsmodel package. So that's exactly the reason why we have imported Statsmodel. If you go at the beginning, we imported Statsmodel, import exponential smoothing. Yes, part of you need Statsmodel for that. So let's run this, and you see a bit smooth version, right? Doesn't look very smooth though, but you can find a bit more smoother version if you change this parameter, okay? So now we have taken 3 period, right? It's a 3 period moving average, but you can make it 5 period and 10th period and so on. And if you increase the period, actually it will look smoother, right? And let me increase it to 20, let's say. It will be even more smoother, as you can see, right? There are less jumps, right? Sharp increase and sharp decrease. For returns data, for return data, it does not make much sense actually. It's more sensible to have this moving average plot for the prices data rather than the returns data, but nevertheless you can also see that. So let's try to see if we increase it to 10, what happens to the moving average plot for returns. Does it look smoother, right? It looks much smoother, right? Isn't it? Increase to 20, even smoother, I would say. Yes, and let's increase further, maybe 30 this time, even smoother, right? So that's what it is. And so moving average also is used to forecast time series, right? If you're familiar with time series forecasting, that's where we use moving average. So it's not just for data exploration, but also for forecasting. Moving average can be used, but we're not going to cover forecasting, time series forecasting in this one. But for exploration, we can certainly use moving average. Then we will use exponential smoothing. So exponential smoothing is also very similar to a simple moving average smoothing, but the difference is that in exponential smoothing you give more importance to the nearer observations, or the only the observations preceding the given time series point. So for example, is of a given time, for example, is t, will give a higher weight to t minus 1 than t minus 2, and then the weight for t minus 2 would be higher than t minus 3, and so on. So that exactly is what is exponential smoothing. You give higher weight to the nearer observation or closer observations in that period. But in simple moving average smoothing, the weight is exactly the same for all the observations, right? Here also we need the Statsmodel, so we have imported. So what we'll do is that we will simply use this simple exponential smoothing functions. I'm not going to go to the details of what exponential smoothing is. You can read it up on Wikipedia. It's basically just taking average, but with some sort of exponential average, I would say, and then doing it that on a rolling basis, right? So you will have as many data points, but it will be combining more than just one observation, right? So here what we do is that we would like to plot the exponential smoothing plot as well as the initial plot without exponential smoothing, and we'll see how they look like, right? And here we use some of the smoothing function actually. So you can actually change it accordingly, and then we have optimization also. So if you do not provide the smoothing level, the parameter, then it will automatically find it for you, the optimal one. But we have kept it as false, but you can also keep it as true. If you keep it as true, then the algorithm itself will find the best fitting curve or the best smoothing level for you. But at 0.1, let's see how it looks like. So this is how your exponential smoothing looks like, and we have compared it with the actual data. So actual data is our red, and the smoothed one, the exponential smoothing one, is basically the blue line, you can see, right? Let's increase this to 0.1, for example. Let's see how it changes, right? It's very similar now. So if you really want to a much smoother one, then you will have to decrease the smoothing level. It's also called the alpha parameter, yeah. But what we can also do is that, and let's say make it true, and then algorithm will find the actual what is best suited for this data. Okay. Okay, so there was an issue with the syntax. Let's run this again. Yeah, so now it is able to find out what is best suited for this data. So yeah, if you want that, you have to use optimize equal to true. And then next what we'll do is that we will explore using the lag plot. So lag plot is used to check if the series or the time series is random or not, and that's very important in time series forecasting, because if a series is random, is very random, you simply can forecasting. You cannot build forecasting model on a random time series data. But if you find it to be non-random, you can certainly use time series modeling techniques to forecast future values. For that we will be importing Pandas, we'll be importing lag plot function, and then using lag plot function we will try to plot the lag plot. Okay, and this is how it looks like. So lag plot is basically a plot between the yt and yt plus 1, basically yt and yt minus 1, either way is fine, right? You just plotting with respect to the previous lag, and you see that there is a linear trend. That means it's certainly not random. If it was random, you won't see a pattern, but you see a linear pattern, so it's definitely not random. You can fit a linear line to this trend, right? And you can see that, right? It's a 45-degree slope, so there is certainly some pattern in this data set. That's important to know. So it exhibits linear pattern, as I said, and it's strongly non-random, and it also suggests that you can fit an autoregressive model to this pattern. I'm not going to go to the details of what autoregressive models are, but if you're familiar with the time series forecasting, you must have heard about AR model. So you can fit an AR model to this data. And then the next thing we'll see is the autocorrelation plot. Autocorrelation is about correlation between the lags, and autocorrelation plot is also used to know whether the time series data has some pattern or it's completely random, right? So before you start building models in time series, you actually will be interested to know the autocorrelation plot as well. And what we do is that we import autocorrelation plot from Pandas, and we plot that. Syntax remains pretty much same like the last one, this EG syntax, and what you see is that if there was no correlation, right, there is absolutely no correlation between your time series with its lags, then this blue line will be hovering around this 0, right, within the 95-99 confidence bounds. So if the blue line is within that confidence bound, then it's random. You simply cannot fit any time series model. But it does show that there is indeed a high level of correlation between the lags. So you can build an autoregressive model or a moving average model, even an ARIMA model, right? And then the next thing and the last thing we like to see here is the partial autocorrelation. Well, partial autocorrelation is slightly different from autocorrelation. It's also something that measures the correlation of the time series variable with its lags, but the only difference here is that you take out the intermediate lags, right? So if you're familiar with time series modeling, you can, I mean, you have the idea about what partial autocorrelation is, but the essence here is that you take out the intermediate lags between yt and yt minus k, where you take out the k lags in between yt and yt minus k. And that's important to know because it's more like a conditional autocorrelation. So partial autocorrelation is conditional autocorrelation, and you should know that in order to find out the order of the AR model, okay, autoregressive model or ARIMA model. So when you build that kind of a model, you have to know that information, and partial autocorrelation is very useful. So we'll also use the Statsmodel, like how we use for autocorrelation, and we'll use the plot PSEF and provided like for how many. So I talked about k, right? So what is the k here? So here I provided k equal to 5. That means I want to take out the k, the 5 intermediate lags between the time series, and I like to see how it looks like. So you will see whether to choose for AR1 or AR2 or AR3 model. In ARIMA, whether it's ARIMA 111, 112 or 21, 2. So that order is something that you get to know by looking at the ACF autocorrelation function or autocorrelation graph and the partial autocorrelation function. So these are some of the things that you can do to explore time series, any kind of time series, but also financial time series. And we'll take few more financial time series to see how you can explore the data more. And you don't have to go into modeling part to be able to understand the pattern in the financial time series. You can certainly understand a lot from it just by doing this exploratory data analysis. Without building any time series model, you can know a lot about the financial time series.